Okay, and for the, we will use the eigenvalues and eigenvectors. Wait a minute. Okay, so we will use the eigenvalues and eigenvectors. And can you hear me?
Yes.
Okay. For finding the P D P inverse factorization. So we will have a matrix A, and then we will factorize it into P D P inverse. So where P will be the matrix obtained by the eigenvectors. So if, for example, if A is an n by n matrix, so P will be the matrix with having the n n eigenvectors. Okay, and where D will be the diagonal matrix, having diagonal elements as the eigenvalues. So lambda 1, 0, 0 up to the last term, 0, lambda 2, 0, and then up to here, 0, 0, and then it will be lambda n. Okay, so n will be an n by n matrix. P will be also an n by n matrix, and then P, and then we can take its P inverse. So this type of formulation can be proved very easily, and it has been done in the book. For the proofs, then you can see the textbook. So let's see its application, and then we can show it. First of all, we will verify that we'll verify that if it works or not. So as an example, we will see we have this vector A. Sorry, we have this matrix A, 3, 1, 1, 3. And if we have this matrix A, and then we have found that its eigenvectors are 1, 1 and 1 minus 1. So you can find these eigenvectors, okay? And then its eigenvalues are the diagonal elements of this diagonal matrix, 4, 0, 0, 2. So its eigenvalues are 4 and 2. So corresponding to these 4 eigenvalue, the eigenvector is 1, 1. Corresponding to this eigenvalue 2, the eigenvector is 1 minus 1. So we can represent these eigenvalues and eigenvectors into these formats. So eigenvectors in the form of the P vector, which is a square matrix 2 by 2, and eigenvalues in the form of a diagonal matrix in which the diagonal elements are the respective eigenvalues. So now we need to verify. Okay, whether this relationship is true or not. So for this, we need we have P, we have D, but we need to find P inverse. So P inverse is the inverse of this matrix 1, 1, 1 minus 1. So how we can find the inverse? So for a 2 by 2 matrix, the quick way is to find the inverse by this method. So first we take the determinant 3 by 3, 3 by 3, and minus 1 by 1. And this matrix, for this matrix, these two terms, these diagonal terms interchange. So both are actually 3 and 3. So by interchange, they will still be 3 and 3. And the reverse diagonal terms will be will change in sign. So this will be -1, this will be -1. So the P inverse matrix will be 9. P inverse matrix will be then 9 minus 1. Okay, 9 minus 1, that is 8, 1 by 8. Okay, so it is the matrix A is 3 1 1 3. So actually, what I have made a mistake. I should not have taken the inverse of matrix A. I should have taken the inverse of matrix B. So I made a mistake over here. So I should erase it. Yeah, and I should take the inverse of P matrix. So it is 1 into -1, 1 into -1, minus 1 into 1. So 1 into 1. And then these 1 and -1, these diagonal elements will interchange. So -1, 1. So this is the quick method for finding the inverse of a 2 by 2 matrix. And then these one values will change in sign, -1 and -1.
So we just changed the sorry for the dumb question, but we just changed the signs of all of the values by -1, or we should change only like by diagonally.
Yeah, so interchange these diagonal elements and
Okay, okay.
and change the signs of these reverse diagonal elements. But this is the shortcut method or the quick method only for 2 by 2 matrices.
Okay.
So just as a reminder, if A is A, B, C, D, then A inverse is 1 over AD minus BC, D, A minus B minus C. Yeah, so just for the reminder. So A and D, they change the places, and B and C, they change the signs. So minus B minus C, and then AD minus BC is the determinant, 1 over the determinant. So in this way, the inverse of a 2 by 2 matrix can be quickly found. So that is 1, and this is -1, this is -2. So that is 1 over -2. So 1 over -2. So we take minus sign inside, so then that will be 1, 1, 1, -1. Okay, so this will be a convenient form for the P inverse. So now we found, since we want to find PDP inverse, so we can first find PD. So we can first find PD. So what is PD? P is 1, 1, 1 minus 1, and D is 4002. So what will be PD? PD will be 1 into 4, 1 into 4, and then 1 into 0. So that will be 0, plus 0. Okay. Then it is 1 into 0, 0, 1 into 2, 2. And then 1 into 4, that is 4, and minus 1 into 0 is 0. And this will be 1 into 0 is 0, plus minus 1 into 2 minus 2. So what we will get is 4, 4, 2 minus 2. Okay, as a result, we get 4, 4, 2 minus 2. So in this case, there is also a shortcut method for such multiplication. As you can see that the resulting matrix is now 4, 4, 2 minus 2. And the original matrix was having 1, 1 and 1 minus 1. So what has happened is that the first column has been actually multiplied by the first diagonal element. Okay, so when we are multiplying a diagonal matrix from the left, okay, when we are multiplying the diagonal elements from the left, then we can see that the resulting matrix will be the one in which the first column will be the one that will be the result of the multiplication of the first diagonal element and the element in the first column. So that means 1, 1, that is the first column, has been just multiplied by 4. So that is a shortcut for this kind of multiplication. And the second column has been multiplied by the second diagonal element, which is 2. Okay, so 2 has been multiplied by 1, that is 2, and 2 has been multiplied by 1 minus 1, that is minus 2. So that was actually just a short, just to show you that uh, as a shortcut you can do like this. On the other hand, if you for example multiply a matrix by a diagonal element, that means the diagonal element is on the left and the matrix is on the right. In those situations, the row elements, first row element will be multiplied by the first diagonal element, and the second row element will be multiplied by the second diagonal element. So that is the other shortcut. So for example, if instead of PD, I could do like dp minus dp inverse. So then what I will get is 4, 0, 0, 2, and then P inverse is uh, actually, yeah, there is 1 by 2 over here. So 1, 1, 1 minus 1, and then that means I can put 1 by 2 over here. So what will happen is that I can, if you can verify it, the first row of this will be 4, 4. That means the first row will be multiplied by the first diagonal element, and the second row will be multiplied by the second diagonal element. So second row will be 2 minus 1. Okay, so you can even check by the proper multiplication as well. So 4 times 1 is 4, 0, so that is 4. 4 times 1 is 4 minus 0, that will be 4. 0 times 1 is 0, and then 2 times 1 is 2. And 0 times 1 is 1, and 2 times 1 is minus 2. So 1 minus 2 is minus, sorry, 0 times 1, so it will be 2 minus 2, yeah, 2 minus 2. So 0 times 1 is 1, and 0 times 1 is 0, and 2 times 1 is minus 2. So it will be like that. Anyway, so this was just as a side discussion. Anyway, so we have now found that PD is this, and now we can multiply PD by P inverse. So PD is 4, 2, 4 minus 2, and P inverse is 1 half of 1, 1, 1 minus 1. So we can put this 1 half outside, and then we multiply these matrices. So 4 times 1 is 4, 2 times 1 is 2, 4 times 1 is 4, 2 times minus 1 is minus 2. 4 times 1 is 4, 2 times minus 1 is minus 2. And then 4 times 1 is 4, and minus 2 times 1 is plus 2. Okay, so now what we get is 1 by 2, 6, 2, 2, 6. So, and then now we divide by 2, so it will be 3, 1, 1, 3. So which is same as a matrix A, which is same as matrix. So in this case, then that means we have verified that the given P and D matrices are indeed the PDP inverse factors. Is it clear?
Yes.
Okay. So in this example, we have verified it that PDP inverse. The next question is that whether we can find that PDP inverse factors or not. Okay. So actually, not every square matrix can be not every square matrix can be factorized into this format. Okay. Uh, yeah, I just forgot to tell you that this process is called. So for example, A is equal to P D P inverse. So that means converting A into P and D matrices. P inverse is of course dependent on P. So converting A into P and D matrices is called diagonalization. Okay, diagonalization. Okay, so this process is called diagonalization. So it is a factorization. It's a kind of factorization, but its proper name is called diagonalization. Okay, so suppose if we have a matrix A is equal to -4, -1, 5, 2. So then can we diagonalize it? Okay, so can we diagonalize it? So for this, we need to find out the uh, eigenvalues and eigenvectors because because I have told that in this case P is a matrix consisting of the eigenvectors and D is a diagonal matrix consisting of the eigenvalues. So which means that if we want to diagonalize it, so we need to find the eigenvalues and eigenvectors. So this means that this process is finding is essentially a process of finding uh, eigenvalues and eigenvectors. However, there are some examples, there are some counter examples in which it is not possible for us to diagonalize it. But that example I will show you later. But first, let's see this example. In this case, I know that it is possible to diagonalize it. So for this, I need to find the eigenvalue, okay, an eigenvector. So if you remember from the last lecture, for finding the eigenvalues, we have a equation determinant of A minus lambda I should be equal to 0, which is called as the characteristic equation, okay. So what is A minus lambda I? A minus lambda I is -4 minus lambda -1, and then it is 5, and then 2 minus lambda. 4 minus lambda, and then -1, 1 to 5, and 2 minus lambda. So this is the A minus lambda I matrix. And what will be its determinant? So its determinant will be -4 minus lambda into 2 minus lambda minus 5 into minus 1. And because for the characteristic equation, that we should equate it to 0. So if you will simplify it, then you will get lambda square plus 2 lambda minus 3 is equal to 0. And if you will factorize it, you will get lambda minus 1 into lambda plus 3. Okay. So by simplification, you get this equation, which is the characteristic standard form of the characteristic equation. It is a quadratic equation. And this quadratic equation, you can easily factorize it into lambda minus 1 into lambda plus 3. So yeah, so 3 plus 3 minus 1 is 2, and then minus 1 times plus 3 is minus 3. So it is fine. So in this way, then we get two eigenvalues, lambda 1 and 3. So therefore, our diagonal matrix will be corresponding to these eigenvalues. So lambda is equal to 1. So we say it as lambda 1, and lambda is equal to minus 3. So we say it lambda 2. Okay, so, or maybe we can say, because minus 3 is, I mean, just it's not necessary, but maybe because minus 3 is less than 1, so maybe we can say that this is lambda 1 and this is lambda 2. So the diagonal matrix will be then minus 3, 0, 0, 1. Okay. So diagonal matrix you can choose like minus 3, 0, 0, 1. Minus 3 is the one eigenvalue, 1 is the other eigenvalue. You can even write it like 1, 0, 0 minus 3 also. That is also correct. But of course, then in that case, your eigenvector will be according to that. So after finding the eigenvalues, we find the eigenvectors. So for eigenvector, we must satisfy this equation, a minus lambda I u is equal to 0, which means that we will make an augmented matrix for a homogeneous system of linear equations. So what is a minus lambda I? So first of all, we will take the first lambda value, which will be minus 3. So it will be minus 3 plus 1, minus 4 plus 1, minus 4, sorry, minus 4 minus minus lambda, because minus lambda, so minus 4, then it will be minus 3. Okay, and only the diagonal elements will be, in this case, will be subtracted by the lambda values because of this identity matrix. So that element will be minus 1 from A, and then that element will be 5, and then this diagonal element will be 2 minus 3. And then for the augmented matrix, for the homogeneous part, you will have 0, 0 over here. So what we have over here is minus 4 plus 3 is minus 1, and then minus 1. And then over here, I will have 5, and then 5, and then 0, 0. So, so this is the system of this equation. And then its echelon form is minus 1, 0. And then we can multiply this first row by 5 and then add to the second row. It will be 0, 0, 0. Remember that in the case of the eigen vectors, you will always find this type of situation over here. So that will not be considered as a mistake. That in fact that is the correct thing. That it will show that your calculations are correct in this case. then in this case you will always get the last equation and the other equations as 0, 0, 0. Okay, and so here you will have now this. So what we are going to find, we are finding u. So if, for example, if the components of u are, say, uh, say u1, u2, or maybe you can say that any other number like k1, k2. So for example, if u1, which is corresponding eigenvector to the lambda 1. Okay, so if u1 is, say, k1, k2, okay, so this first equation will be minus k1 minus k2 is equal to 0. So it means that k1 will be equal to minus k2. So if we take k2 as equal to a free variable s, so it will be minus s. So in any case, you will get the eigenvector in terms of s as, so k1 will be minus s and k2 will be s. Okay, or if you take s as common outside, and then we will get minus 1 and 1. Okay, so even you can write here, you can see that you can change the sign as well. So for example, if instead of minus 1, 1, if you multiply it by minus 1, so the signs will change from 1 minus 1. So 1 minus 1 will be also correct. Okay, minus 1, 1 is also, and 1 minus 1 will be also correct. So we get one eigenvector as minus 1, 1. Okay. The other eigenvector we get from the other eigenvalue. So first of all, here we have used the eigenvalue as lambda 1 is equal to minus 3. If we use the second eigenvalue, so then what will be a minus lambda I? So it will be, so the second eigenvalue is 1. So it will be minus 4 minus 1, that will be minus 5, and then minus 1, and then 5 here, and then 2 minus 1, 2 minus 1, that is 1. Okay, so okay, and then for homogeneous case, now we get is minus 5 minus 1, 0, and then we add this, then it will be 0, 0, 0, 0. So as again we have got 0, 0, 0, 0 in the in this case, so which is normal for the eigenvectors calculation. So now what we get over here is, in this case again we say if these are k1, so if so 5 k1 minus k2 is equal to 0, or if we take k2 is equal to s, then k1 will be minus s over 5, minus 1 by 5 s. So in this case, the eigenvector which we will get is u2 eigenvector.
Давайте без... Sorry.
Yes.
No, nothing.
So we will get s and minus s over 5. Okay. So s and minus s over 5. So it will be 1 and minus 1 over 5, s and then minus 1 over 5. Normally, for the eigenvectors, it is by convention, you do not want to put your answer in the form of fraction. So you can multiply this vector by 5, and then that will be absorbed into this arbitrary constant. So it will, instead, you can also write it like 5 minus 1. Okay, you can also write it like 5 minus 1. Okay, so S1, no, yeah, I think I made a mistake over here, because S2 was, K2 was S, so it should be, yeah, it should come over here. Yeah. So K1 was minus S over 5. Okay. So let me erase. Okay. So K1 was minus S over 5 and K2 was S. So it is then S over here, S over here. So it is minus 1 over 5 and 1. And then we multiply by 5. So it will be minus 1 and 5. Okay, minus 1 and 5. Therefore, in this case, our P matrix, which will be actually the which is actually the U1 and U2. So that will be P matrix will be in this case will be U1 was minus 1 1 minus 1 1 and U2 was minus 1 5. So minus 1 5. Okay, U2 was minus 1 5. So 1 okay, so this is the matrix P. So P is equal to minus 1, minus 1, 1, 1, 5. So remember that in this case, if for example, if you put minus 1, 5 instead of minus 1, 5, if you make it as 1 and then make it as minus 5, then this is also okay. So instead of if you put minus 1, 5, you can put 1 minus 5. That will be also okay. Okay. So now we have found P, and then we have found P, we have found D, and then what we can do is, now I have no space over here, so let me write down the results over here in the next slide. So remember that A was 1 minus 2, sorry, no, not 1 minus 2. A was A was minus 4 minus 1 minus 4 minus 1 and 5 2. A was minus 4 minus 1 5 2. Yeah, minus 4 minus 1 5 2. D was minus 3 0 0 1. So we found D was minus 3 0 0 1. Yeah, minus 3 0 0 1. And then P we found as minus 1 minus 1 1 5. Okay, P we found as minus 1 minus 1 1 5. Minus okay. So from P down, we can find the P inverse. Okay. So by the shortcut method. So what is that? Minus 1 times 5 and then minus 1 times 1. Okay. And it will be 5 and minus 1 will be replaced with each other. So, and then minus 1 will become 1, and then this one will become minus 1. So what we will get over here is, this is minus 5 plus 1, minus 5 plus 1, okay. So it is minus 1 over 4. So it will be 1 over 4, and then I take minus sign inside, so it will be minus 5, minus 1, 1, 1, okay. So it will be minus 5 minus 1, 1, 1, okay. So now you can verify it, okay. So for this verification, First, I will do the P D. Okay, P is -1, -1, 1, 5, and D is -3, 0, 0, 1. So by this, what is going to happen is the first column will be multiplied by -3. So it will be 3 and -3. And the second column will be multiplied by 1. So that means it will remain as -1 and 5. So this will be the result of PD. And now I will take PDP inverse. So PDP inverse. So PD is this 3 -1 -3 5. And then P inverse is -5 -1 1 1, and then 1 by 4 was here. So 1 by 4, I just keep it outside for the time being. So now it is 3 times -5 is -15. -1 times -1 is -1 times 1 is -1. And then 3 times -1 is -3. And -1 times 1 is -1. And here -3 times 5 is 15. And 5 times 1 is 1, 5. And then -3 times 1 -1 is 3. And 5 times 1 is 5. So what I get over here is 1 by 4. So it is -16. This is -4. And this is 20. And this is 8. And now I can divide by 4 each term. So it will be -4. It will be -1. It will be 5. And then it will be 2. So -4, -1, 5, 2, which is the same as matrix A. So it means that we have verified that our diagonalization process was correct. Is it correct? Do you have any question?
No.
Is the process clear?
Yeah.
Okay. So let's see one more example. And this is actually a counter example where it is not possible to find the to perform the diagonalization process. So for suppose if we have a matrix 1 -2 0 1. If we have this matrix 1 -2 0 1. So for if we want to find PDP inverse, then we need to find the eigenvalues and eigenvectors. Okay, U. Okay. So for finding the eigenvalues, so we will write it into the characteristic equation form. So it will be 1 minus lambda minus 2, 0, 1 minus lambda. Okay, and then we will find its determinant, which is 1 minus lambda square, and then we will equate its determinant to 0, because 1 minus lambda square, 1 minus lambda, and then -2 times 0 is 0. So that is -2 times 0 is 0. So what we get over here is 1 minus lambda square is equal to 0, and then 1 minus lambda will be 0, and then lambda will be equal to 1. So it shows that it has this this matrix has only one distinct eigenvalue. So that means in fact it is a double eigenvalue. Okay, so from this eigenvalue, if it is a if it matches well, let's now try to find the eigenvector. Okay, so its eigenvector we can find by the writing it in the form of a augmented matrix. So what we will do is we will subtract this eigenvalue from the diagonals. So from the diagonal, so the diagonal of A are 1. So 1 minus 1 will be 0, and then minus 2 and 0, and then 1 minus 1 will be 0. So we will have this type of augmented matrix in this case for the condition A minus lambda I u is equal to 0. So for this condition, which is used for finding the eigenvectors, so we get this type of matrix. And now in this matrix, what we see is the last row is 0, 0, 0. Okay, this is fine. From the first row, what we get is minus 2 times, for example, if vector u is k1, k2, okay, if vector u is k1, k2 in this case, so then this will be k1, this will be k2, so minus 2 k2 is equal to 0. So k2 is equal to 0. But what about k1? K1 is not in the picture over here. So because 0 times k1, so k1 is actually not there. So this means that in this case, the eigenvector will be only this, u is equal to k2, that is u is equal to 0. So this is a very strange result, because now I think if we multiply a by this 1 minus 2 0 1, so this is 0. So what is this? So this will be actually a scalar actually. This will actually consist of scale. So it is actually now what you have over here is 2 by 2 matrix. This is 1 by 1 matrix. Its scalar product is possible, but its matrix product is not possible. Okay. So for the eigenvalue, for the eigenvector, a lambda, a u should be equal to lambda u. This equation should satisfy. But now in this case, since now the vector eigenvector is just a one dimensional, this type of situation is making us a problem over here. Or even if we consider it as a scalar, so then the result will be a 2 by 2 matrix. Okay, so which is not a good thing to have it over here. So in this case, in mathematical form, what we will say is that the eigenspace associated with this case is one dimensional. So we can say that the eigenspace obtained is one dimensional. Okay, so eigenspace obtained is one dimensional, whereas our initial matrix A is a two-dimensional matrix. Okay, 2 by 2 matrix. So since in this case these two conditions are not matching, A is two-dimensional. Okay, which means that we are talking about R2. Here we are talking about R1. So R2 and R1 are not matching, I think. And these two things are not, these two conditions are not matching. So our final answer is A is equal to 1 minus 2, 0, 1 is not diagonalizable. So this is the answer. Okay, this is not diagonalizable. Okay, so this is the answer. Is it clear?
Yes.
Yeah.
All right. Okay, so this diagonalization process can be used. So diagonalization process can be used for conveniently finding the powers, power multiplication of matrices such as a square, a cube, okay, a4, etc. So for example, if we want to find a square, then we have to write a matrix and then a matrix, and then from row and column, then we need to perform the multiplication. If we have to find a cube, then we have to write it for the third time. However, this type of diagonalization process gives us a convenient way for finding the matrix multiplication. Why? So the answer is in this formulation. So for example, if A is equal to P D P inverse, so which we have seen for one or two examples before, that we can find it. Okay, if we can find A is equal to P D P inverse, then we can find A square as follows. So it will be A square will be A dot A multiplied by A, and then we can write it like P D P inverse. A can be written as P D P inverse, then it will be P D P inverse. And now from here we can write PD as one entity, and P inverse P is another entity. P inverse P is another entity. So DP inverse. So P inverse and P, that is an identity matrix because both are inverse with each other. So this is an identity matrix. So P, it will be P D identity matrix B P inverse. So identity matrix, if we multiply PD with the I, so PD I will be PD, right? Identity matrix multiplied by any other matrix will be that matrix. So it will be PD, and I will be removed. So then D and P inverse. So PDI is equal to PD. And now we get this one. And then from here, D into D, that is D square. Okay, D into D, that can be written as D square, P inverse. Okay, P D square, P inverse. So in this case, A square will be P D square P inverse. So if we want to find the A square, so we need to find P D and P inverse. And then A square will be simply P D square P inverse. So similarly, by this method, A cube will be equal to P D cube P inverse. And any value of K will be equal to P D power K D inverse, P inverse, okay? So, but here the advantage is that D power K and D square, D cube can be found very easily. So for example, if we have D is equal to say A0, 0, 0, B, 0, 0, 0, C. So then we can find D square by A0, 0, 0, B, 0, 0, 0, C, and then we have A0, 0, 0, B, 0, 0, 0, C. So what we will get is A square, and then everything else will be 0. 0 and then B square, everything else will be 0, 0, 0, and then C square, everything else will be 0. So D square can be very easily found by just squaring the or taking the same power of the elements on the diagonal. So it means that D cube, D power K will be equal to, in this case, will be equal to A power K, 0, 0, 0, B power K, 0, 0, 0, C power K. So this which means that if we want to find a power 5, so simply what we will do is we will find A and P and P inverse and then D. And then for A power 5, we will simply take the power of D as equal to 5. So this process can be then used to very conveniently take the powers of the matrices. Okay, power multiplication of the matrices. Okay, so I think the time is up for today. So this topic for the diagonalization, we have there's a little bit more discussion left for this diagonalization process. So that we will do in the next lecture, and then we will also start about the complex eigenvalues and eigenvectors in the next lecture as well. So that topic. So that's all for today, and then I will see you in the next uh, uh, week. On the